Welcome back. In the previous lecture, we built a conceptual framework for mass spectrometry, the five-module architecture, the vacuum requirement, and the five key performance metrics. We touched briefly on the ion source and called it Module 2, but we left the details for today. This lecture is entirely about Module 2, the ion source. Every mass spectrometry experiment lives or dies by how well this one component performs. Let's begin. Six objectives for today. First, classify sources as hard or soft. This is the single most important distinction in the field. Getting this right is half of method development. Second, describe the mechanism of each of the six sources, not in gory detail for every one, but enough that you understand why each method exists and what analytes suit it. Third, selection. Given an analyte, pick a source. This is the practical skill you'll use in any lab that runs MS. Fourth, predict the ions. Every source produces a particular pattern of ions: protonated, sodiated, deprotonated, multiply charged, and various adduct. You need to know what to expect so you can interpret a spectrum. Fifth, deconvolute multiply charged envelopes. This is a specific mathematical skill unique to ESI that we'll work through with a concrete example. Sixth, recognize and mitigate the main practical problems. Ion suppression is probably the single most common source of frustration in LCMS work, and knowing how to deal with it will save you a lot of time in the lab. Here's today's lecture path outline. As usual, we'll start with some theory, some applications, and some practice problems. Okay, so the fundamental distinction. So the defining feature of any ionization source is how much internal energy it deposits into the analyte ion. That one variable controls almost everything that follows. Hard sources deposit a lot of internal energy. The resulting ion has so much excess energy rattling around in its vibrational modes that it falls apart. Bonds break, fragments form, and what you see is a rich pattern of fragment ions. The molecular ion itself is often weak or even invisible because it simply doesn't survive the ionization process. This is great if you want to figure out an unknown structure. Each fragment is a diagnostic clue. It's terrible if you want to know the molecular weight because you may not see the molecular ion at all. The classic hard source is electron ionization at 70 electron volts, which we'll study in detail in a few minutes. Soft sources deposit very little internal energy. The ion forms, collects a proton or a sodium, or loses a proton, and survives essentially intact. The spectrum is simple, sometimes just a single peak. Molecular weight determination is therefore trivial. Quantitation is easy because you concentrate all the signal in one peak rather than spreading it across fragments. But if you need structural information, you have to go to tandem mass spectrometry, MSMS, where you deliberately fragment the ions in a later stage of the instrument. We'll cover tandem MS in Lecture 5. The plot on the right sketches the internal energy distributions. ESI has a sharp distribution centered at about 0.3 electron volts, essentially thermal. CI is slightly hotter, maybe 1 electron volt on average. EI is a broad distribution centered around 4 electron volts with a long tail. Here's a crucial number. A typical carbon-carbon single bond has a dissociation energy of about 3.6 electron volts. The ESI distribution doesn't even reach that threshold. Essentially, no fragmentation occurs. The ESI, the EI distribution sits well past it, so fragmentation is the rule, not the exception. Everything else in this lecture is essentially an application of this one idea. Source selection map. This map is the single most useful diagnostic when choosing a source. Two axes, polarity on the horizontal, molecular mass on the vertical. Each source occupies a region. Electron ionization sits at the bottom left. Small, nonpolar, volatile, thermally stable analytes. Think of GC amenable compounds, hydrocarbons, pesticides, small drugs, fragrances. If your analyte could run on a GC, EI is usually the right choice. Chemical ionization overlaps with EI, but it reaches slightly higher masses and gives softer spectra with clearer and cleaner molecular ions. APCI and APPI are both atmospheric pressure methods used with LC. APCI covers mid-polarity compounds, drugs, lipids, steroids. APPI extends into non-polar territory that would otherwise require GC. Polycyclic aromatic hydrocarbons, crude oil components, some pigments. The niche is real but narrower than ESI's. ESI occupies a huge territory on the right, polar and ionic compounds, from small pharmaceuticals up through proteins in the 100 kilodalton range. The big advantage of ESI is multiply charged ionization, which makes even very large molecules accessible on modest mass range analyzers. MALDI is the specialist for singly charged high mass analysis, intact protons, synthetic polymers, biopolymers. It sits at the top. A rough heuristic for a new analyte, first ask about polarity. If the compound has ionizable groups or is very polar, start with ESI. If it's volatile and nonpolar, go EI. If it sits in between or is thermolabile, APCI is often the right answer. If it's very large, MALDI is the specialist. We'll refine this framework at the end of the lecture. Electron ionization, the classic hard source. Electron ionization is the oldest and still the most widely used ionization method for small molecule GCMS work. Let me walk through how it works. A sample in the gas phase enters the source. A heated filament, usually a rhenium or tungsten wire, emits electrons thermoionically. These electrons are accelerated through a potential of 70 volts across the ionization chamber. They pass through the gas phase sample, and occasionally one of them knocks an electron off an analyte molecule. The result is a molecular radical cation, M plus dot with a plus charge, which has lost one electron and therefore has an unpaired electron. That's the radical part. And it's crucial to the fragmentation chemistry we'll study in Lecture 4. The 70 electron volts number is worth explaining. In the very early days of EI, people noticed that ionization cross sections, the probability that an electron of a given energy will ionize a molecule, rose from threshold, peaked somewhere about 50 and somewhere between 50 and 100 electron volts, and then declined. 70 was picked because it sat near the peak, because the cross section is relatively flat in that region, so small variations in electron energy don't change the spectrum much, and because, frankly, the first commercial instruments used 70 volts, and everyone matched them. The real payoff of that arbitrary choice is universality. An EI spectrum of toluene measured at 70 electron volts on a brand new instrument today is essentially identical to one measured at 70 electron volts in 1960. This reproducibility is what enables spectral libraries. NIST maintains a library of over 250,000 EI spectra, and the Wiley library has over 600,000. You run your unknown at 70 electron volts, the software does a library search, and for a well-known compound, you get a match in milliseconds. This is a massive practical advantage that no soft ionization method enjoys to the same degree. The diagram on the right shows the geometry. Filament on the left emits electrons that cross the ionization chamber. The sample enters from above. Ions are extracted downward by the repeller into the mass analyzer. The electron trap on the right collects electrons that made it through. Let's have a look at a real EI spectrum. Methanol is about as simple as molecules get, and even for methanol we see substantial fragmentation. The molecular ion at the mass to charge ratio of 32, that's CH3OH plus radical cation, is present, but is about 66% as intense as the base peak. The base peak at MZ31 is the ion CH2OH plus, formed by losing a hydrogen radical from the molecular ion. This is the oxocarbenium cation, stabilized by resonance through the oxygen lone pair. It's so stable that it forms preferentially. Then we see smaller peaks at MZ30, MZ29, MZ15. Each one is diagnostic of a particular loss. The MZ15 peak is the methyl cation formed by breaking the carbon-oxygen bond and keeping the charge on the carbon. The point I want you to take away is, even for tiny methanol, the molecular ion is not the biggest peak. You see fragments. This is the signature of hard ionization. And here's the upside. This pattern is reproducible. If you run this sample on any EI instrument anywhere in the world at 70 electron volts, you get the same peaks at the same relative intensities within about 5%, which means a library search is reliable. NIST's top match for this pattern comes back as methanol with a match factor above 900 out of 1,000. That's effectively a confirmation. We'll develop the interpretation rules in Lecture 4. For today, just note that the pattern molecular ion present, but not dominant, several characteristic fragments, library matchable. Chemical ionization was invented in 1966 by Munson and Field at ESSO, now Exxon. The motivating problem was that EI was destroying the molecular ion in many petroleum hydrocarbons that they were trying to characterize. They needed a softer method. The CI idea is elegant. Take an EI source and fill it with a reagent gas of roughly 1 millibar, 1,000 times higher pressure than usual EI operation. The electron beam still ionizes things, but at this higher pressure, it ionizes the reagent gas before it reaches the analyte, because there's so much more reagent. The methane reagent, the initial ionization, produces methane radical cation CH4 plus dot. But methane radical cation is extremely reactive and quickly reacts with the neutral methane molecule to form CH5 plus, a protonated methane, and a methyl radical. This CH5 plus is a powerful proton donor. When an analyte molecule M comes along, CH5 plus donates a proton to it, forming the protonated analyte MH plus and regenerating neutral methane. This proton transfer is thermodynamically gentler than electron ejection. It deposits much less internal energy in the analyte, so the ion doesn't fragment. Different reagent masses give different softness. The relevant parameter is the gas phase proton affinity, Pa. Methane has a low Pa, so transferring a proton from CH5 plus to the analyte is very energetic. You might still see some fragmentation. Ammonia has a very high Pa, so transferring a proton from NH4 plus is barely energetic at all, extremely soft ionization. As you move from methane to isobutane to ammonia, spectra get cleaner, but the range of analytes you can ionize at all gets narrower. Ammonia only protonates compounds that are themselves very basic. Ci is the right choice when Ei gives you no molecular ion and you need to know molecular weight. Historically, it was the go-to soft method for GC amenable compounds. Today, for most libraries, APCI and ESI have largely replaced Ci, but Ci is still standard equipment on most standard GCMS instruments. Electrospray ionization is the workhorse of LCMS. Electrospray is the most transformative development in the analytical mass spectrometry in the last 40 years. It's what makes modern LCMS possible, and it's what let us put proteins into mass spectrometers for the first time. Here's the idea. Push a solution, typically the effluent from an LC column, through a narrow capillary held at several kilovolts relative to ground. The electric field at the capillary tip is enormous. At the tip, the liquid forms a conical shape called the Taylor cone, named after Sir Geoffrey Taylor, who worked out the fluid dynamics in 1964. From the tip of the Taylor cone, tiny charged droplets spray off. As these droplets move through the hot nitrogen drying gas stream, solvent evaporates from them. The droplets shrink, but the charge can't leave. The droplets become more and more highly charged. Eventually, they reach the Rayleigh limit, the point at which Coulomb repulsion between the charges and the droplet exceeds the surface tension holding the droplet together. The droplet falls apart into smaller droplets, a process called Coulomb fission, and those smaller droplets go through the same cycle again. After a cascade of these fission events, you're left with very tiny charged droplets, eventually so tiny that only one analyte molecule is in the droplet. Through mechanisms still debate the ion evaporation model and the charge residue model, the analyte is released into the gas phase as an ion, typically carrying one or more protons. The key special feature of ESI is that it gives you multiply charged ions from large molecules. A protein the size of insulin doesn't appear as a single peak at MZ 5800. It appears as a cluster of peaks at MZ 1000, 1100, 1300, corresponding to the protein carrying various numbers of protons. This is great because it means even a modest mass analyzer with a range of only MZ 2000 can measure a protein of mass 50 or 100,000 Daltons so long as the protein carries enough charges. This is the single reason modern biological MS exists. The diagram shows the essential geometry. Capillary on the left, high voltage, spray emerging, droplets shrinking and fissioning, finally entering the MS through a sampling cone on the right, and the hot nitrogen drying gas flowing across to help evaporate the solvent. The Rayleigh limit and Coulomb fission. Let's make the Rayleigh limit concrete because it governs everything that happens in an ESI droplet. Rayleigh derived this expression in 1882 for the stability of a charged liquid droplet. The maximum charge that a droplet of radius r can carry without becoming unstable is 8 pi times the square root of epsilon 0 times gamma times r cubed. Epsilon 0 is the vacuum permittivity. Gamma is the surface tension of the liquid. The scaling is important. The maximum charge goes as r to the 3/2 power. So as a droplet gets smaller, the maximum charge it can hold drops quickly. Let's compute for water droplets. Surface tension of water is about 0.073 newtons per meter at room temperature. A 5 micron droplet, which is roughly where ESI starts, can hold up to about 1.4 million elementary charges. That's enormous. A 1 micron droplet can hold about 125,000 charges. A 100 nanometer droplet can hold about 4,000 charges. A 10 nanometer droplet, which is the scale at which ions are released, can hold about 126 charges. Now, here's what happens in an actual electrospray. A droplet starts at maybe 5 microns with a certain charge. Solvent evaporates, the droplet shrinks. At some point, the charge exceeds the Rayleigh limit for its current size. The droplet undergoes fission. It throws off a swarm of much smaller droplets that carry away about 15% of the charge, but only about 2% of the mass. The parent droplet has shed enough charge to be stable again and continues to evaporate. The daughter droplets each go through their own cycles. After perhaps 10 such cycles over a few milliseconds, you've gone from micron scale droplets to tens of nanometers, and the charge per droplet has dropped from millions to hundreds. At that scale, each droplet contains only one or a few analyte molecules, and the analyte ion can escape into the gas phase. This cascade is why ESI produces such clean gas phase ions from a solution. The solvent evaporation and charge reduction are exquisitely gradual, so almost no kinetic energy is transferred to the analyte. The analyte ion emerges essentially cold. Here's a worked example, deconvoluting an ESI protein spectrum. This is the single most important practical skill that ESI gives you that other methods don't, deconvoluting a multiply charged spectrum. Let's walk through the problem concretely. We have a protein. ESI gives us two peaks, one at MZ500 and 1.3, and one at MZ300 and 34.454. We've been told the charge states 2 plus and 3 plus, and we want to recover the actual protein mass. The setup for an ion that's the protein plus Z protons carrying Z plus charge, the MZ is the mass of the protein plus Z times the protein mass, all divided by Z. The proton mass, by the way, is 1.00728 Daltons, not 1. That's the mass of H plus, which is H minus its electron. Don't confuse it with the hydrogen atomic mass, which is about 1.00783. The difference is the mass of an electron, which matters at the ppm level. Rearranging, m equals z times the mz value minus z times the proton mass. Plug in for z equals 2. 2 times 501.3 is 1002.6. Subtract 2 times 1.00728, which is 2.0146. We get 2000.585 Daltons. Plug in for z equals 3. 3 times 3, 34.5. 4 is 1003.62. Subtract 3 times 1.00728, which is 3.022. We get 1000.598 Daltons. The two numbers agree to within 0.013 Daltons, which is 13 ppm. That's excellent agreement, and it confirms both the mass and the charge state assignments. We report the protein mass as 1000.59 plus or minus 0.01 Daltons. The plus or minus comes from the spread between the two independent measurements. Why do we need two charge states? Because from a single MZ peak alone, you cannot determine the charge. A peak at MZ500 could be a singly charged molecule of mass 500, or a doubly charged molecule of mass 1000, or a triply charged molecule of mass 1500. Only multiple peaks across an envelope let you solve for both M and Z simultaneously. A common pitfall is that if you misassign the charge state of a peak by 1, say you call it 3 plus when it's really 4 plus, you get a mass that's off by roughly 33%. That's a massive error. Always cross-check with a second charge state, and for a real protein work, modern software uses the entire envelope of often a dozen or more charge states to converge on a mass with sub-Dalton accuracy. ESI in practice. Let me close the ESI section with two practical issues you'll meet most often when running electrospray. First, adducts. In positive mode, the common ion form is protonated, M plus H, because electrospray is run in a slightly acidic solvent with formic acid. But you'll also see sodium adducts, potassium adducts, ammonium adducts if you're using an ammonium buffer, and sometimes dimers where two analyte molecules cluster with one proton. Each adduct shifts the MZ by a characteristic mass, which is useful because if you see peaks at the right spacings, you can confirm that they all belong to the same analyte. A peak at MZ 279 that has a partner at MZ 301, exactly 23 Daltons higher, is telling you the parent is very likely an M plus H at 279 with the sodium adduct M plus Na at 301. The sodium and potassium adducts are often unwanted because they split your signal across multiple peaks. Sources of sodium include glassware, low-grade solvents, and even the skin oil in your fingertips. A common method development activity is to clean sodium out of the system by switching to clean solvents and polypropylene vials. In negative mode, you usually see deprotonated ions, M plus, M minus H, and sometimes formate adducts if formic acid is in the mobile phase. Negative mode is great for acids, phenols, and some halogenated compounds. Second and most seriously, ion suppression. This is the single biggest practical problem in ESI-based quantitation. Ion suppression happens when other compounds collude and with your analyte and compete for ionization in the source. The competitors can be phospholipids from biological samples, surfactants from glassware, buffer salts, anything surface active. In a contaminated sample, you can easily lose 30 to 90% of your signal compared to the same concentration in clean solvent. That obviously destroys your calibration. 4. Mean mitigations. 1. Chromatographic separation. Make sure the analyte elutes away from the matrix interferences. 2. Isotope labeled internal standard. If your IS is essentially the same molecule as your analyte, it experiences the same ion suppression and the ratio stays constant. This is why deuterated internal standards are the gold standard in quantitative LCMS. 3. Simple sample cleanup, solid phase extraction, protein precipitation, dedicated phospholipid removal plates. 4. Just dilute the sample, often called dilute and shoot. If your sample is clean enough and your analyte concentrated enough, diluting out the matrix works well. And finally, the post-column infusion test. This is a diagnostic experiment. You infuse your analyte at a constant concentration post-column while injecting a blank matrix on the column. The signal you see as the matrix elutes through the detector tells you minute by minute how much suppression the matrix is causing at any retention time. If your analyte elutes in a suppressed region, you move it. The next one is MALDI. MALDI, matrix-assisted laser desorption ionization, was invented essentially simultaneously by Karas and Hillenkamp in Germany and by Tanaka in Japan in 1985. Tanaka shared the 2002 Chemistry Nobel with Fenn for his work. The problem MALDI solves is the same one ESI solves, getting a large, fragile biomolecule into the gas phase as an ion without destroying it. The solution is different, though. In MALDI, you mix your analyte, typically a protein or a peptide or a polymer, with a large molar excess of a small organic compound called the matrix, 1,000 to 1 or even 10,000 to 1. You spot this mixture onto a metal plate and let it dry. As the solvent evaporates, the analyte gets incorporated into the growing crystals of the matrix spread thinly throughout. Then you fire a UV laser pulse at the spot. The matrix is chosen so it absorbs strongly at the laser wavelength. Nitrogen laser at 337 nanometers was the classic choice. Solid state ND neodymium YAG lasers at 355 are more common now. The matrix absorbs the photon, gets vibrationally hot, and a tiny volume of matrix crystal desorbs explosively into a plume of vapor. Analyte mixtures embedded in that volume come along for the ride. In the plume, proton transfer happens. Matrix molecules are chosen to be acidic, and the basic amine groups of proteins grab protons from the matrix molecules during the short-lived high-density plume phase. The matrix matters. Alpha cyano 4 hydroxycinnamic acid, abbreviated CHCA, is the standard for peptides. Cinnapic acid is used for intact proteins. Dihydroxybenzoic acid, DHB, is good for glycans and synthetic polymers. DAN, diamino naphthalene, is used for lipids. Picking the right matrix for your analyte class is a real skill. The big features. MALDI gives singly charged ions almost exclusively. Unlike ESI's multiply charged envelope, so a protein of mass 50,000 appears as a single peak at MZ 50,000. You need a mass analyzer with large MZ range, which is why MALDI is almost always paired with time-of-flight instruments. TOF has theoretically unlimited mass MZ range. MALDI is pulsed, which is actually perfect for TOF because TOF is inherently pulsed too. The laser pulse and the TOF extraction happen on the same nanosecond timescale. MALDI tolerates small amounts of salt better than ESI does, which is useful for biological samples. But MALDI has its own peculiarity called sweet spots. The crystal surface is heterogeneous and different parts of the spot give wildly different signal. Modern MALDI TOF instruments search for sweet spots automatically by rastering the laser across the spot. One niche that Amaldi now owns is clinical microbiology. Every major hospital microbiology lab now uses Amaldi to identify bacteria from colonies. You pick a colony, smear it on a plate, add matrix, run the instrument, and get a species identification in about a minute based on the pattern of ribosomal proteins. This has revolutionized clinical microbiology in the last 15 years. APCI and APPI. APCI is atmospheric pressure chemical ionization is the second major LC source after ESI. It's essentially a CI clone at atmospheric pressure using a corona discharge rather than heated filament to create the reagent ions. Here's what happened. LC eluent enters a nebulizer where it's broken into a fine aerosol. The aerosol passes through a very hot vaporizer tube, typically 400 to 500 degrees Celsius. By the time it exits the tube, all the solvent has evaporated and the analyte is a neutral gas phase molecule mixed with the vaporized solvent. Then a corona discharge needle sitting at several kilowatts ionizes the surrounding gas. The corona ionizes nitrogen, oxygen, and essentially the solvent vapor, especially the solvent vapor. The cascade of charge transfers eventually produces protonated solvent clusters, H3O+, and it hydrates are the usual protein donors in a water methanol or water acetonitrile system. These protonated solvent ions transfer a proton to the neutral analyte, giving M plus H. The key difference from ESI, and this is the sentence to remember, is that in APCI, ionization happens after the solvent is completely evaporated. The analyte is already in the gas phase when it gets ionized. In ESI, the analyte is still inside a shrinking charge droplet right up until the moment it's released as a gas phase ion. What this means practically is that APCI and ESI have different strengths. ESI is better for polar ionic and very labile analytes, things that would decompose if you heated them to 500 degrees. APCI is better for moderately polar analytes that don't have any ionizable groups. Steroids are a classic example, as are some vitamins and lipids. These compounds don't protonate well in the droplet environment of ESI because they don't have basic sites, but they do protonate well in the gas phase chemistry of APCI. APCI also tends to be less sensitive to the specific kinds of ion suppression that hit ESI hard. Phospholipids, for example, cause massive ESI suppression, but much less APCI suppression. For that reason, in regulated and bioanalytical work with serum or plasma samples, APCI is sometimes chosen over ASI, specifically to sidestep the phospholipid problem. There is one caveat. APCI can't handle thermolabile compounds because of the high vaporizer temperature, and it doesn't produce multiply charged ions, so it's useless for large protons. For those, you stick with ESI. APPI, atmospheric pressure photoionization, is the newest of the LC sources dating from around 2000. Bruins and Sayegi developed it independently. The concept is instead of using a corona discharge to ionize things, you use a krypton UV lamp. The lamp emits a 10 to 10.6 electron volts. A molecule with an ionization energy below 10 electron volts can absorb the photon and directly eject an electron, forming molecular radical cation. The trick is that many common LC solvents, water, methanol, have ionization energies above 10 electron volts, so they're transparent to the lamp. Only the analyte ionizes. That makes APPI somewhat selective. Direct APPI works well for molecules with ionization energies below about 10 electron volts. That includes polycyclic aromatic hydrocarbons, which are notoriously nonpolar and notoriously hard to ionize any other way. PAHs are the signature APPI analyte class. For molecules with higher ionization energies, you can use dopant-assisted APPI with deliberately add toluene or anisole to the mobile phase at 1 or 2%. The dopant absorbs the photons, forms a radical cation, and then charge exchanges with the analyte. This extends the APPI method to a wider range of compounds. The major industrial niche for APPI is the petroleum and fossil fuel industry, a field called petroleonomics. Pioneered by Alan Marshall at the National High Magnetic Field Lab in Florida, uses APPI coupled to FTICR mass spectrometry to resolve tens of thousands of individual molecular formulas in a single crude oil sample. No other combination of source and analyzer can do this. The molecules are too nonpolar for ESI, too non-volatile for GCMS, and too numerous for anything less than FTICR resolving power. Outside that specialist niche, APPI has a following among people who analyze steroids, pigments, some cannabinoids, and certain classes of drug metabolites. But in most routine LCMS work, ESI is the default, and APCI is the usual second try. APPI only enters the picture when both of those fail. Choosing a matrix. Let me consolidate your choices into a decision tree you can use for any new analyte. You start at the top and ask if the analyte is thermally stable and volatile enough to survive a GC oven. If yes, small molecules, go straight to EI. You'll get a rich spectrum and library matchable identification. If no, you're doing LCMS. Next question is the molecular weight above 10 kilodaltons. If yes, MALDI. Those large molecules benefit from MALDI's singly charged spectra and MALDI-TOF's unlimited mass range. ESI is also an option for proteins because of multiply charged ions, but MALDI is often simpler for mass determination. If molecular weight is below 10 kilodaltons, the next question is the analyte polar or ionic? Does it have an acidic, basic, or permanently charged group? If yes, amines, acids, sugars, peptides, many pharmaceuticals, ESI is the default. It's the most widely supported, most robust, most general purpose LC source. If the analyte is non-polar, uh, neutral, mid-polarity, no ionizable groups, then you ask whether it's polycyclic aromatic hydrocarbon or petroleum component. If yes, APPI is specialist. If no, steroids, vitamins, lipids, APCI is the usual choice. There's one more rule that overrides all of this. If you're unsure, try ESI first, both in positive and negative mode. ESI has the widest analyte range of any LC source, and in most labs, it's the default mode of operation. If ESI fails, then switch to APCI. If that fails, try APPI. This sequence covers almost every real-world LCMS problem. One final caveat. The decision tree is a starting point. In practice, you need to consider the instrument you have access to, the mobile phase your chromatography demands, the regulatory context, and the specific matrix. These can all shift the answer, but the tree gets you 90% of the way there. Let's apply what we've learned to five real analytes and make it concrete. First, paracetamol and plasma. Paracetamol, acetaminophen, Panadol is a small polar amide. It has a phenyl group and can deprotonate and a nitrogen that can protonate. It's thermolabile, so you can't heat it too much. It's in plasma, so we're doing LC with the aqueous mobile phase. ESI positive mode is the obvious answer. The molecule protonates well in the amide nitrogen, giving a clean M plus H at MZ 152. This is a standard method used in every therapeutic drug monitoring lab. Second, polystyrene oligomers from molecular weights of 2 to 50 kilodaltons. Polystyrene is a non-polar polymer, so no ionizable groups, no heteroatoms, just carbon and hydrogen. It's also pretty large. ESI would struggle because polystyrene doesn't protonate. APCI would struggle for similar reasons. MALDI is the answer. Dissolve the polymer in THF with ditheranol as the matrix, and MALDI-TOF gives a clean oligomer distribution with each peak separated by the monomer unit. This is the standard polymer characterization method. Third, crude oil polycyclic aromatic hydrocarbons. These are thousands of different non-polar compounds all packed together. They're too non-volatile for GC. They don't ionize in ESI. They don't ionize well in APCI. APPI with a toluene dopant is the standard, and for the highest resolution work, you pair APPI with an FT ICR analyzer. This is the classic petroleonomics experiment. You can get 30,000 unique formula assignments in one run. Fourth, a ribosomal protein complex at 2.6 megadaltons. This is a huge non-covalent assembly. You want to measure the intact mass, which means preserving the non-covalent interactions. The technique is called native ESI. You buffer exchange the complex into ammonium acetate, spray it into the source under gentle conditions, and get multiply charged ions at very high charge states, typically 50 to 100 charges on a megadalton complex. This is cutting edge work, but well established in the structural biology community. Fifth, organochlorine pesticides in animal tissue. These are things like DDT, dieldrin, chloridane, small nonpolar thermally stable. They're GC amenable, so GCMS with EI is the standard. The EI spectra are library matchable, so you can identify unknowns, and the characteristic chlorine isotope patterns help confirm class. This is the established method in every environmental testing lab worldwide. Notice how each choice flows from the analyte properties. You don't pick ESI because it's fashionable, you pick it because the molecule is polar and ionizable. Source selection is always the first decision in method development, and getting it right is half the battle. Industry applications. So industry applications, here's a quick tour of the different sources, the map onto the pharmaceutical and biotech, ESI is the workhorse. Small molecule drug, QC, metabolite, ID for drug development, and so on. All ESI. MALDI-TOF is a specialist for intact biopharmaceuticals. And APCI has a niche for steroids, vitamins, and lipid-based formulations. Food safety and agriculture. Here the picture is split. Polar pesticides like glyphosate and neonicotinoids go to ESI. Mycotoxins and antibiotics also ESI. But the organochlorine pesticides, chlorpyrifos, DDT, dieldrin are still routinely measured by GCMS with EI because the compounds are volatile and the EI spectral libraries are so thoroughly validated by decades of use. Clinical and forensic, ESI dominates for therapeutic drug monitoring. Then going to environmental, we look at ESI for polar emerging contaminants such as PFAS, which has been a big story over the last several years. Here are your end of lecture practice problems. Please go through them and attempt them before solutions are posted later in the week. and a summary of next lecture where we will be looking at mass analyzers and detectors. Thank you for listening.